All right. So, okay. So in the last class, if you remember that we were discussing the which problem, the race around condition. Race around condition that occurs when the J and K both are 1 1 and the clock pulse is also 1. Okay. And I mentioned that there will be 3 solutions for this race around condition, because whenever you plug J and K both as 1 1 at high voltage and clock is also high, so the output of that flip flop always racing. Means previously if it was 0, so at the next it will become 1 and then 0, then 1, then 0, then 1, 0 1 0 1 0 1 0 1 till your clock pulse is high. So this is the race around condition. Okay, we have drawn the figure of that. So should I continue with that? Okay. Okay, so this was your JK flip flop. And we were discussing the race around condition. And what is that? What is the race around condition? So when there is your clock pulse is high, J is 1 and K is also 1. In this situation, what happens? Your outputs of the JK flip-flops is in racing condition. Output races actually. And we have another term for that is toggling. Okay, so let me call this as my clock pulse. And when J is high and K is high, and previously, let's suppose this is my Qn, this is my output of the flip-flop, that is Q. So it was 0. So as it see the high in the clock pulse, high level clock pulse, so it becomes 1. And J and K both are connected. So again it will become 0, then 1, then 0, then 1, and then 0. And similarly again for the high level of this clock pulse. And this condition is called racing. And here if you see at the end of this clock pulse you have a high. So this will continue, because this low of this clock pulse means whenever our clock pulse is 0, we stated that for that condition our flip-flop is in memory state. Our flip-flop is in memory state. Okay, so this will the output will be whatever at the time of this level. If it was 1, so it will continue to 1 till your clock pulse is low. And when it see there is a high in clock pulse, it will toggle the output. So it was 1, now it will become 0, and similar. So this condition, so this problem is known as race around condition. And what are the solution for this race around condition? Because why it is coming? If you remember the truth table for JK flip-flop, so if my J and K is written here and both are 1 1, so the Qn plus 1, that is the output of flip-flop, will be Qn bar, isn't it? And Qn bar means whatever the condition, whatever the previous output was, it will change, it will complement to that. That's why we are having this clock race around condition in the JK flip-flop. And what is the solution for this race around condition? So the solution can be, as I mentioned in the last class, the first solution can be, here see, if I said this, yes, if this is my T on and the total time period of this clock is t. Okay, so total time period is what? T. And t on is the time when my clock is high. Okay, and this is the propagation delay, TP, we defined. What is TP? TP is nothing but time taken by the flip-flop to generate the output. Time required by the flip-flop to generate the output. Okay, so can we get rid of this race around condition? So what is the solution? If why this is occurring? Because for the high clock pulse we have a less time period, that is propagation delay. We will call it propagation delay. Okay, so the first solution to race around condition. The first solution can be if TP becomes greater than this T on, then this race around condition will not occur. And in a competitive exam, they may ask when the race around condition occurs. So when the race around condition occurs, when my T on is greater than TP. This is the condition, this is the time duration for which the race around condition occurs in the JK flip-flop. So if we can do this, then our problem will not be in the JK flip-flop. And it is not possible actually. It is not possible because we cannot increase the propagation delay of any flip-flop, and that is actually the time taken by the gates. Because in the circuitry of JK flip-flop, what we have gates. Okay, so and that will delay our total overall response, because here we are talking only for one bit. When we will dealing with the 64 bit or the higher number of bits, the total propagation delay, if you want to increase that will lead the sluggish response in the system. Correct? So we cannot do this. So second solution, we can have a master slave arrangement. Master slave flip-flop. And what is this master slave flip-flop? We will see here. And that is very important topic here, master slave flip-flop. Okay, so first question is why we are using master slave flip-flop? To get rid of this race around condition. Okay, we'll see how can we draw a circuit that will not generate this race around condition, and we will call that JK master slave flip-flop. Okay, so here we have NAND gate, we have a clock pulse here, and this is my Q, and again I have the similar Again, I have the similar structure. You will having a clock pulse here. Okay. Now, how to remember this circuit? How to remember this circuit? What I have drawn here, this is the structure where we used in the SR, isn't it? And when we take the output and connect it to here, this will become the JK flip-flop. Do you remember this? Okay. So here, and that's why we are having this race around condition. What happened when you have this arrangement? And this output is connected, the input of this, and here you have this one. So whenever you apply 1 and 1 here at the JK flip-flop, one of the output of this and NAND gates are the output of this. One of the input of this NAND gate is the output connected from the from here. Correct. That's why this race around condition is occurring. Let's suppose I applied 1, and according to the truth table, I should have the complement of the previous condition. So whenever it was 0, immediately it will become 1. And then again, because this is connected in the input of this NAND gates. So it's see, we have a new input. Both of the NAND gate what will they see? They will see there is a change in the input. So again, they will change it because of this condition. So what we will do in the master slave flip-flop, we will not connect this outputs immediately in the inputs of this NAND gate. Isn't it? What we'll do, we'll connect from this position. So and here also okay. Now, so we'll define these inputs later. Now see how the clock pulse is connected. Clock pulse is connected in this manner. You will put a NOT gate here to activate the second one. Now see this part, I will call this as a master. This is my master circuit. And this is my slave circuit. Because slave, what is doing? It is taking the outputs of this master as an input. That's why. It is following the output of the previous one. Slave circuit is taking the outputs of the master circuit as the input. It will work according to the output of the master. That's why the name suggests master and slave. Okay. Now we'll see the problem and the analysis. We will do the analysis for this. Now I will define this Q as QS, and this will be QS bar. S stands for, no, we will define this as M, master, and this will be QS and QS bar. Okay. So now let us consider few things. See, because this is connected in this fashion, because the first one, the master is directly connected to the clock pulse. However, our slave is connected to by a NOT gate. Okay. So whenever there is a high in the clock pulse, this circuit, master circuit, will be active. And whenever there is a low in the clock pulse, this slave circuit will be in active position. This will be working. So I will write it whenever clock is 1, clock is 1 means the QM, the output of QM will be active. Or we can write this, the master will be active. And the slave circuit will be in memory state. Okay, it should be very clear why it is in memory state, because you are applying 0 at the clock pulse, and whenever you apply 0, you see the truth table for the JK flip flop or SR flip flop. Whenever there is a 0 in front of clock pulse, regardless the condition of the inputs, the output will be, or the next state will be as the similar previous one, that is the memory state. That's why we'll call it memory state. And whenever there is a clock 0, so this master will be in memory state and the slave will be active. Correct. Now we'll see the working of this. We have a clock pulse here. Okay, this is my CLK. Now I assume that J is equal to 1 and K is also 1. How do this circuit behaves? So now this is my QM and we have a QS. Okay, now we applied 1 and 1 in front of this inputs. 1 and 1. See, let's previously we assumed that Q was 0, QM was 0 and QS was also 0. It means that you have 0 in this position and 1 in this position. QM bar will be what? 1? Correct. And QS also 0, so QS bar will be 1. Now, see, this is, we have QS as the input of this NAND gate. Correct? QS bar as the input of this NAND gate. It means you have 1 in this position and 1 is also applied and clock pulse is high. We are dealing at this position. Clock pulse is high. So this will be in memory state. This whole circuit, the slave circuit will be in memory state. Okay. And here all of these 3 inputs are 1, 1, 1. However, we have 0 in front of this because we assume QS is 0. And that is feedback connected here. So any of the input of this NAND gate is 0, so output will be what? 1. And all of these inputs are 1, so output will be what? 0. And see, this is my latch circuit, NAND latch. And remember, whenever there is a 0 and 1 in front of latch, so what will be the output? Say it. No.
0, 1.
Check it. It will be 1. Remember always, otherwise you will be in problem. For the latch, the output or QM will be 1. If you don't believe, see your the truth table of NAND gate, NAND latch actually. So QM immediately become 1. So I will draw the circuit for this. Now I will have a QM1. And what happened to this? What happened to QS? QS, because we have applied high clock pulse, for the high clock pulse, in front of this slave circuit, you have 0. It means this will be in memory state. The output of this QS will be in memory state, isn't it? So it will remain 0 for this high period, and it will become 1. As you have the low level at your clock pulse, the moment you have the low level at your clock pulse, this slave circuit will become active. It means this will see the outputs of this master circuit as the input. So now what is the input? of this, what will be the input for slave circuit? QM, that is 1, and it is active for this low pulse. Correct? So now I have, because what do you have? 1 and 0, isn't it? And for 1 and 0, this is my SR circuit. Do you remember this? This is my SR flip-flop. And for set and reset flip-flop, whenever you have 1 at S, it means this will set. So I can draw like this. Now the moment you have a clock high clock pulse, this circuit will become inactive, means it will go in the memory state. Okay, so it will continue. However, this was for the low level, this circuit was in memory state. Okay, so for the low level, this will be in memory state. The moment it see the high in the clock pulse, it will change accordingly. Okay, so now what do we have at the QS? QS is high, and it is connected here. So all these three, because we are applying 1, 1, and 1. So all these three of the input will be 1, 1, 1. So output will be what now? 0. And one of the input will be 0 according to that. So 0, any of the input is 0 of the NAND gate will become 1. And for this NAND latch, you will have 0. 0 at QM. So immediately this will become 0. Correct? And it will continue till this high clock pulse. And for the low clock pulse, that master will be in memory state. Correct? So this will continue till this position. However, as the slave sees a low clock pulse, it should change its position or the previous position, previous output. So what will be the next step? So it will see the QM, because QM is connected as the input, and which is 0 now. So if it is 0 and this should be 1. Now this is my 0 and this should be 1. So according to this 0 and 1, this SR latch or SR flip-flop will be 0. So it will become immediately 0 for this. And for the high clock pulse, this QS will be in memory state. So whatever the previous condition, whatever the previous output, that will continue. Okay, now accordingly, this will again change. So is it easy or tough? Okay, whatever it is. See, now we don't have toggle or racing condition in a high period. See there. For a particular time period of the clock pulse, we have a stable state here. Okay, and what we are interested, this will be our final output. So we'll call this as a J and K. So this will become my now JK master slave flip-flop. And the final output will be this. Whenever you apply this clock pulse, it will be working for only low level. The output you will get at the low level of this clock pulse. So we have seen here this master slave flip-flop. Now can we do another solution? Can we have another solution for this? Yes, we have. What is that? See, we were having the problem for this whole area. If we can able to reduce this area, so we don't have any this problem anymore. So we can do one thing. There are 3 types of triggering. What do you call this? Clock pulse. Whenever you apply clock pulse, and according to the clock pulse, your circuitry is working or is in active mode, that is called a triggering, because you are triggering that circuit. Okay, what you are doing, you are triggering that circuit. So according to the position of this clock pulse, we define 2 types of triggering. And what are they? We'll see here. Okay, two types of triggering. First is level triggering. And the second is edge triggering. You see this clock pulse, it has two things. First is level and this edge. Okay, so till now what we have seen that our circuit is triggered, or it will change its transition, or it will change its state after looking at this level. So can be defined, it should change its state after looking this edge. If this circuit see a high edge or the rising edge, whenever the clock pulse goes from 0 to high, I want to design that level or that mechanism that will change the circuit. So this is called the triggering. Okay, so here we have these two types of triggering. First is level triggering, and the second is edge triggering. When my circuitry or the flip-flop changes its position, or they do a transition in its state by looking this level, that is called a level triggering. And if they change their position or they change their states after applying this edge, this is called edge triggering. So we do have two types of triggering for each of this. First is high level triggering, and the second is low level triggering. And for this, we have a positive edge trigger and the negative edge trigger. Correct? I can also define that when my clock pulse goes from high to low, at this position my flip-flop should be active, or it should change the position. It should change the previous state. So that will come under the negative edge trigger. So now we'll apply the negative edge triggering in JK flip-flop, and we will see what happens. So you have a JK flip-flop here, and we have a edge-triggered, negative edge-triggered clock pulse. And each of these has a specific symbol, because this is represented in this form. The high-level triggering is represented in this form. If you put a bubble sign in front of this will become low-level triggering. And if there is a triangle, this is called positive edge triggering. And if you put bubble in front of this triangle, this will become negative edge triggering. Okay, this is my positive edge, negative end, and this last one. So now we'll see what happened when we apply a negative edge triggering to JK flip-flop. I will put 1-1 because we are very interested in this 1-1 combination of this JK flip-flop. And I say it will change its state when it see a negative edge. Negative edge means from high to low. So now my J and K are both 1-1. And previously if it was 0, so it will continue till this position, because now I see a negative edge here, isn't it? So I can define this, and it will continue till the next negative edge, that is here. So now it will change. I can see here. Okay. So now this result we obtained due to the negative edge triggering. And if you can see here, both my output of this master slave flip-flop and the negative edge triggered flip-flop are same. Isn't it? So it means we have another solution of this race around condition. So we can use the edge triggering. So this is very important question because it comes in your question, final examination. What is this master slave flip-flop? What is the race around condition? And what are the solution for that? How the race around condition occurs? What are the timing condition for this? Of course, यदि वो ऑनलाइन होगा और ऑन पेपर होगा तो थ्योरी आएगी. Okay. So this was the concept for master slave flip-flop, and it is used for the to get rid of this RAC condition. This may be the solution, one of the solution for the race around condition. Okay. So now we'll see the next flip-flop. Okay. See, in JK flip-flop, if we are dealing with this 1-1, okay, so can we do one thing here? We can connect both the inputs and we can apply only one input here. We can connect because we are applying 1-1. What we are interested, sometimes we are interested in toggling. We want our circuit should toggle from the previous condition. We want the state from the complement state from the previous one. So we will apply 1-1 in front of J and K. So can we do this arrangement? We will connect both of these inputs of JK flip-flop in this manner. So this will become a T flip-flop. And now T stands for what? Toggling. Generally, it is known as T flip-flop. Okay, so now you have a clock pulse here and the output. I'll write T. Okay, so now first of all, write the truth table for this T flip-flop. If you apply 0 in front of clock pulse, regardless of the condition of the T input, there will be a memory state. Now, if you apply 1 or for the high level of the clock pulse, if you apply 0 at the T, 0 means what? Reset, not reset. It will be in memory state for JK flip-flop because both of the JK inputs are connected to each other. Means you are applying 0, it will go 0, 0 in front of JK flip-flop. So 0, 0 will what? Memory state. And for 1, toggle. Correct? Now this was the truth table for. Now we are back to our flip-flops. This is the last flip-flop we need to study. What we have done, SR flip-flop, JK flip-flop, D flip-flop, and this will be a T flip-flop. Yes, of course. Now what we'll do, the characteristic table. So for the characteristic table, always remember this, because whenever you do the conversion of flip-flop, we will doing this after this completion of this flip-flop. and that is also very important topic. Always you will find one or two questions in theory to convert flip-flops. Okay, we need to write characteristic table at that time. So how do you start writing characteristic table? Characteristic table means the characteristic of this flip-flop. So the output or the final of this table will be what? The Qn plus 1. That we are interested, the next state. Okay, and that will depend on what? The previous state and the input. Always. So there will be 4 combination. If the output, the previous one was 0 and you apply 0, so the Qn will be what? 0, because this is in memory state. If you apply 1, it will become 1. If you apply 0, it will become 1. If you apply 1, and previously if it was 1, so it will become 0. This is very easy, isn't it? Okay. So can you write the Boolean expression in terms of Q and T? Think it and write. Isn't it? XOR, right. And what will be the excitation table? How do you proceed for the excitation table? Whenever you write excitation table, excitation means what? Whatever the excitation you have for the circuitry. Excitation means inputs. So at the output, at this level, you have this input. However, you will be writing this excitation for the states, outputs, previous one and the next one. So here also you do have 4 states. So 0, 0, it means it was 0 applied. If 0, 1, say it. 1 applied, and here 1 applied because the state has changed. And again 0 because this is in memory state. So T again, T will be what? Qn XOR Qn plus 1. This is your T flip-flop. Okay, so now we will proceed to conversion. We will convert one flip-flop to another one. So what is your point of view? Should we continue with this or should we take in the next lecture? I don't find any logic because you have another lecture after 5, right? If you can go to hostels, then it is okay to continue this in next lecture. However means you have a lecture on 5, so what will you do for the 20 minutes? Okay, no problem. We'll start in the next lecture. However, I will give some introductory part on then. So for the conversion of one flip-flop to another flip-flop, write few points. First of all, the question will be like, you need to convert JK flip-flop into another flip-flop. Say it is SR flip-flop. The question is, convert JK flip-flop into SR flip-flop. So we'll take an example here. Example or the question is JK flip-flop to SR flip-flop. Correct? So the question we obtained here, the convert JK flip-flop into SR flip-flop. So what is the important steps you need to take? First of all, you need to find out which is the required one. What is the required module? Which flip flop is required here?
JK.
No, that is wrong. It's a required one. We need, because
SR.
SR, actually it will be SR. And what is the available flip flop?
JK.
Okay, correct. That is JK. The third step will be, you will writing the characteristic table for the required one. So in this case, you will write a characteristic table for what? SR. The fourth one is, you will be writing the excitation table for the available. And the last step is, you will writing Boolean expression in terms of the Qn and the inputs of which one? Let me think it. No. This is your required one. Yes, correct. So these are the steps you need to follow whenever you do conversion from one flip-flop to another flip-flop. Okay. So we'll continue this from the next lecture.
सर
Yes.
सर ये QN गिवन वाले का है या रिक्वायर्ड वाले का?
ये तो गिवन वाले का है, अवेलेबल का. This all these steps will be very clear whenever we will solving the questions. Okay. And how do you remember for which you need to write characteristic table, for which you need to write excitation table? Either you ratta mariye inka. Otherwise, you can do, there is a R in this required. So there is also a R in the characteristic table. There is no R in the excitation table. Right? So whatever require, you can apply this method. Either you can choose any other methodology to remember this. All these steps will be very clear whenever we will solving the questions. Okay, there is no rocket science. Okay, no problem. So we will stop this lecture here and we will continue with this conversion of flip-flop in the next lecture after Deepavali. On the Wednesday, I will be not available here, so I will be on leave. So that class will be postponed, and possibly that class will be on Saturday, 13th of November. Whether it is a working Saturday or the total off Saturday, whatever it is, we'll announce that. In case if you will not available, I will do that class in online mode. That's good. That is your choice.